Welcome to The Explainer. Today, we are diving straight into the invisible backbone of modern web authentication. If you've logged into basically any modern web application recently, chances are you've interacted with a JSON Web Token, or JWT, without even realizing it. They are the lightweight, silent messengers powering access across the entire internet right now.
Because we're dealing with a pretty dense cryptographic subject today, we're going to follow a clear roadmap. First, we'll meet the JSON Web Token. Then we'll look at JWTs in the wild, dissect the anatomy of a token, and finally, break down the differences between JSON Web signatures and JSON Web encryption. Let's get into it.
Section 1. Meet the JSON Web Token. Let's establish exactly what this thing is in practical terms.
So what are we actually talking about here? At its core, a JWT is just a standardized container. It safely passes assertions, which the industry calls claims, between different parties. Think about it. When two servers are talking over the web, or your browser is hitting an API, they're communicating in extremely space-constrained environments like URLs or HTTP headers. A JWT takes all your complex identity and authorization data and squishes it down into a compact, URL-safe, printable string that can travel effortlessly anywhere on the web.
And, this need for compactness and safety didn't just appear out of thin air. Before JWTs, it was kind of the Wild West. Companies were building their own ad hoc, frankly clunky solutions to pass data around. So back in 2011, the JSON Object Signing and Encryption, or JOSI, working group formed. Their entire mission was to standardize this process to support interoperability. They wanted a simple format that everyone could just agree on, and that eventually evolved into the JWT standard we rely on today.
Moving right along to Section 2, JWTs in the wild. Let's look at where you actually see these things in action.
Why do we care so much about JWTs? Well, two words: stateless sessions and federated identity. Take a look at this. Companies like Auth0 use JWTs to provide a unified interface, acting as a centralized authorization server. Instead of you, as a developer, having to build separate custom login flows for Google, Twitter, or your own database, your application can just trust a service like Auth0 to handle the heavy lifting.
Here's how that federated flow actually plays out. Picture this. You try to access a protected dashboard. The resource server says, "Hold on," and redirects you to the authorization server, which then hands you off to an identity provider to log in. Once you successfully authenticate, you're redirected back to the resource server carrying an access token. And guess what? That token is almost always encoded as a JWT. It grants you access without ever exposing your actual password to the resource server. It is incredibly efficient.
All right, Section 3, Anatomy of a Token. Time to get this thing on the operating table and crack it open. At first glance, a raw JWT looks like absolute gibberish. Seriously, it's just a massive string of random letters and numbers. But under the hood, it's actually three very distinct JSON elements: the header, the payload, and the signature. Each of these parts is individually converted to a URL-safe version of base64 encoding and then stitched together with periods. The header tells us what kind of token it is and the algorithm used. The payload holds our actual data. And the signature, that locks it all down.
Now, inside that payload, we have what the spec calls registered claims. Notice how ridiculously short these acronyms are? We're talking sub for subject, X for expiration. This intentional brevity is absolutely crucial because it saves precious bytes when you're sending these tokens over spotty mobile networks or packing them into browser cookies. You can totally add your own custom claims, but these registered ones are universally understood across the industry.
Section 4, JSON Web Signatures, or JWS. How do we actually know we can trust the data inside the token?
Think of a JWS, a signed JSON Web Token, is a tamper-proof nightclub stamp. It proves to the bouncer that you are exactly who you say you are, but third parties standing in line can still see the stamp on your hand. The signature simply proves the data hasn't been maliciously altered since it was created. But here's the kicker. Anyone who gets their hands on the token can decode that base64 string and read your payload. If you put a user's shopping cart items or personal info in an unencrypted JWT, anyone intercepting it can read exactly what's in there.
So how do we create that signature? This brings up a massive cryptographic distinction between symmetric and asymmetric keys. HMAC uses a symmetric shared secret. That means the server issuing the token and the server validating it have to share the exact same password. If that secret ever leaks, it's game over. Anyone can forge a token. RSA, on the other hand, uses asymmetric keys.
Only the server holding the tightly guarded private key can create the signature, while any client holding the widely distributed public key can verify it. It is absolutely perfect for one-to-many communication.
But listen, careless implementation will still lead to vulnerabilities. One classic attack you need to watch out for is signature stripping. An attacker just deletes the signature portion entirely and changes the algorithm header to the word none. If your backend library isn't strictly configured, it might just accept this forged, completely unsigned token as valid. You also have to fiercely protect tokens from cross-site scripting, where malicious JavaScript steals tokens right out of local storage, and cross-site request forgery, where attackers trick the browser into sending the token automatically.
Which brings up a vital question for your own web apps. If a signature just validates data to prove it wasn't tampered with, does it actually keep things like sensitive profile information private from prying eyes? Spoiler alert, absolutely not. Decoding the token reveals the data in plain text. And that perfectly tees up our final section, JSON Web Encryption.
If a JWS signature is just a nightclub stamp for authenticity, JWE is a lock safe inside an armored car. It encrypts the token so thoroughly that it is entirely opaque and completely unreadable to anyone intercepting it. If you have to send highly sensitive data through a client's browser, JWE ensures that only the intended backend recipient can actually read what's inside. But to use it, you have to understand a fundamental, almost mind-bending shift. Encryption completely flips the asymmetric flow compared to signatures. With JWS signatures, the producer uses a private key to sign, and consumers use a public key to verify. Data flows private to public. But with JWE encryption, the producer uses the public key to lock the safe, and only the server holding the private key can open it and decrypt it. The data flows public to private.
Because asymmetric math is incredibly CPU heavy, JWE pulls off a really clever trick for performance. It generates a blazing fast, symmetric key to encrypt your payload, and then uses the slower asymmetric key just to encrypt that symmetric key. Because of this added complexity, an encrypted JWE actually has 5 elements separated by dots, instead of just 3. You get your protected header, the encrypted key itself, an initialization vector for randomness, the actual encrypted ciphertext, and an authentication tag to guarantee the ciphertext wasn't messed with.
Let's put the pieces together sequentially. First, the system generates that random content encryption key. Next, it locks that key up using the recipient's public key. Then, it grabs the random initialization vector, optionally compresses your payload, and finally encrypts the data to produce the ciphertext and the authentication tag. Encode all those pieces into base64 URL format, separate them with dots, and boom, you have your JWE string totally safe for transport across the open web.
But hang on, there's a catch. Because JWE allows anyone with the widely available public key to encrypt data, how do you actually know who sent it to you? If you want the benefits of both proving exactly who sent the data and keeping it strictly private from everyone else, you use nested JWTs. You literally take a JWT that has been signed with JWS and use that entire string as the payload for a brand new encrypted token using JWE. The recipient strips away the encryption layer first and then validates the signature tucked inside. And that brings us to the core of understanding modern token architecture. As we wrap up this explainer, I want you to look at your own application's architecture and ask yourself a serious question. Are your JWTs merely validating user data with signatures, leaving it completely exposed for anyone to read? Or, when the data demands true privacy, are you actually protecting it with encryption? Understanding the crucial difference between JWS and JWE is the absolute key to building truly secure stateless web applications. Thanks for diving in with me, and we'll catch you on the next explainer.